This is Unit 3 Practice Exam A for Math 1100. So question 1, to find dy dx, we follow the differentiation rule for exponential functions. The derivative of e to the u is e to the u times u prime. So the derivative is e to the u times u prime. So the derivative of u prime would be the derivative of this, which is 15x to the fourth. So the derivative 15x to the fourth multiplied by e to the power of 3x to the fifth. For question 2, we use the differentiation rule for natural log, which is the derivative of natural log of u is 1 divided by u times u prime. Now, there's two ways you can approach this one. I'll show you the first way is just to use the rule straight up. So the derivative dy dx is 1 over u times u prime. And then there are usually things to simplify using this method. So the 20 and the 5 simplify to 4. X to the third cancels with 3 of those. So we get 4 divided by x. So there's one way. The other way to think about this is to use rules of logarithms. So it's 5 times x to the fourth. It's not 5x to the fourth power. So what we could do is use the product rule, natural log of 5 plus natural log of x to the fourth, and then bring that 4 down in front of that second logarithm. And then we can do dy dx. So the derivative of natural log of 5 is 0. 4 is a coefficient, so it's just going to stay 4. And then derivative of natural log of x is 1 over x, so we get 4 over x. That's another way of thinking about doing the derivative of natural logs. And I tend to use that way more to simplify logarithms as far as you can before differentiating, because it usually makes it a little easier. Question 3. Now this involves taking the derivative of an exponential function that doesn't have a base e. So remember, the derivative of e to the u is e to the u times u prime, but that only applies to a base e. If we have any other base, then there's a formula. So the formula is the derivative with respect to x of a to the u is natural log of a times a to the u times u prime. So we can use that formula here. So the base a in this case is 3, so the derivative of y with respect to x is natural log of 3 times 3 to the power of x to the fourth. And now we do the derivative of u, which is 4x to the third. And there really isn't a standard order that these are supposed to be written in, so that would be an acceptable way to leave that answer. Now, the other way to approach that problem, if you're worried about remembering a formula, because this formula won't be given on the exam, this would be something that's expected to be in memory. The other way to approach this is to rewrite the exponential function instead of a base 3, rewrite it as a base e, and then give it an exponent of natural log, because those two are going to cancel each other out anyway. And then use rules of exponents and rules of logarithms. The power rule specifically says you can take the power, move it down to the front. Rather than moving it to the front, which is typical, I'm going to just move it down off to the right side. So this could be e to the natural log of 3 times x to the fourth. And then if we did rules of differentiation now for a base e exponential function, so that's what we have as a base e. The derivative of a base e exponential function is itself, so this could be e to the natural log of 3 times x to the fourth. But now we do the derivative of the exponent, which is natural log 3 times 4x to the third. Now, simplifying that, we would need to put this back together so that the x to the fourth is an exponent back on the 3. So this would be e natural log of 3 to the power of x to the fourth times natural log of 3 times 4x to the third. And then you would cancel out the e and the natural log exponent, which means 3x to the fourth. 3 to the power of x to the fourth becomes a term like we have here. So you get the same answer. Maybe a little longer way of doing it, but you don't have to memorize a formula. So that's also a possibility. Question 4, the derivative of natural log, like we did for question 2, is 1 over u, but that only applies to natural log. If we have log base 4 or log base any other base besides base e natural log, then what I'd recommend is to do the change of base formula. So I would rewrite the original equation, so not any derivatives yet, the natural log of x squared divided by the natural log, in this case the base is 4, so it would be the natural log of 4. And then I would rewrite that one more time. Rather than dividing by the natural log of 4 and having that be a quotient, I would move the natural log of 4 to the front as a coefficient, like that. And then one more thing I would do is this exponent right here, use the power rule, move it down in front. So 1 divided by the natural log of 4 times 2 natural log of x. So when we do the derivative now, the 1 over natural log of 4, that's just a constant value, so it's a coefficient. 2 is a coefficient, so that's just going to stay as a coefficient. So I'm going to combine those as 2 over the natural log of 4. And then we do the derivative of natural log of x, which is 1 over x. So then the final result is 2 divided by x times the natural log of 4. Question 5 really just is bringing in some previous rules of differentiation just to help all of our students keep current. So this one would obviously involve the product rule, but it also is going to involve differentiating a base e exponential. This one will use a quotient rule. So these two questions are meant just to help practice the product rule and quotient rule. So if we think about the two factors here of this product, we have that factor and this factor right here. So this could be like f and g. So remember the derivative of a function f times g is f prime. So the derivative of f prime would be the derivative of that first factor there. So that would be 20 x to the fourth. So that's f prime times g plus g prime. So now if this is g, the derivative of e to a power, the derivative of e to a power is e to that power multiplied by the derivative of that power. So we have f prime times g plus this whole thing here is g prime, so we need to multiply this by f. So this is f. So that's the product rule, f prime g plus g prime f. Now if we simplify a little bit here and look at what both sides of this expression have in common, by both sides, here's the divider here that separates it. So here we have a left side and a right side. What are some terms that they both have in common that can be factored out? Well, this side has an e to the power of x to the third. This side also has an e to the power of x to the third, so that can be factored out. 20 and 3 don't have any common factors, but x to the fourth and x squared has a common factor of x squared. So I'm going to factor out an x squared and e to a power of x to the third, which for here will leave 20x squared And then from this side, it will leave 4x to the fifth, and there's a 3 there in front of it, 4x to the fifth plus 5. So then if we simplify right here, the 3 times 4 makes 12 times 15, and then 20x squared. So writing the terms in descending order, we're going to have a 12x to the fifth plus 20x squared plus 15. Okay. Now question number 6, we're going to obviously have a different approach because it's a quotient rule. So dy dx. So we have the bottom function multiplied by the derivative of the top function minus the top function multiplied by the derivative of the bottom function. Now the bottom function is an exponential, so the derivative of an exponential base e is itself multiplied by the derivative of the exponent, so 25x to the fourth, all divided by the square of the denominator. Now as we look to simplify in the numerator, this minus sign here separates to a left half and a right half. So if we look for common factors, we have e to a power 5x to the fifth here, same thing there, so that's a common factor. Between 8x and 25x to the fourth, the common factor there would be just x. So I'm going to factor out of that numerator an x and e to a power 5x to the fifth. What that's going to leave is 8 from here minus 4x squared plus 3 times 25x to the third divided by e to a power of 5x to the fifth squared. Now, we have e to a power 5x to the fifth. Well, there's two of them because it's squared, and there's one of those powers here. So this factor is going to cancel with one of those factors. And I'm also going to distribute this 25x to the cube into here as I write the final. So remember, this is going to cancel with one of these. And then I'm going to distribute the 25x to the third into that. So the final result could be x times 8. Now this is going to become 25x. 25 times 4 is 100, so minus 100x to the fifth. And then 25 times 3 is 75, so minus 75x to the third. Divided by e to the power of 5x to the fifth. And if you wanted to distribute the 8 or the x into there, that's fine. Or if you kept it out, not a huge deal. Question 7, what's meant to happen here is to recognize that there's some simplifying of logarithmic terms that need to happen before you differentiate. So this is not a derivative. I'm just rewriting natural log instead of a fifth root, giving it a power of 1/5, and then using the power rule to bring that 1/5 down as a coefficient. Because that'll make finding the derivative much easier. So that 1/5 is just going to stay 1/5 coefficient, and then the rule for differentiating a logarithm, natural log, remember, is 1 over u times the derivative of u, so that would be 6x. So then we have a final result there. And again, you can multiply the 5 into the parenthesis or keep it out. Doesn't really matter. Now with question 8, this is the phrase we're looking for. It's decaying or growing, in this case decaying at a rate proportional to the amount present. That phrase, like we've said, tells you that the model you're going to use is the exponential growth model, in this case exponential decay. And because it's decaying at a rate proportional to the amount present, we know it's going to follow that exponential growth model. So again, y represents a future amount, c is the initial amount, k is the relative growth rate, t is time. So what we say here, or what we see here, is 5.3 thousand years ago, the initial amount was 1,091.7 milligrams. The current mass is 109.9 milligrams. So if now we have 109, so that's what I'm going to put in place of y, and then the initial amount 5.3 thousand years ago was 1,091.7, and that took 5.3 thousand years. So now we can use this exponential growth or exponential decay model to solve for k, that relative growth rate, because we need that to be able to answer this question: what will the mass be in 5.1 thousand years? So we solve this by getting k by itself. It's an exponent. You can't solve for a variable if it's an exponent. Remember, so you cancel the base, and we cancel the base e using a natural log. But first, you have to get rid of that coefficient, so divide. Now we take natural log. And if we do a natural log here, the base is going to cancel out. The natural log will cancel with the base e, so it's just k times 5.3. And then we divide by 5.3. So k we can get an estimate for k at around negative 0.43319. Now, since it's up to you as a student if you want to, when you use the formula, use the exact form of k or an approximate form. Anytime you use an approximate form, remember it's going to mean that your final result, since you use an approximation early on, is going to be slightly off, and that's okay. There's a level of allowable error here since we're using some approximations. So if you are going to use an approximation, try to use as many decimals as you can. I'm going to use the approximation because it's easier to plug into a formula. So this is k. So the formula now, if we're talking about present time, so the future amount, presently there's 109.9 milligrams. The relative growth rate is this. And then I'm going to have 5.1 thousand years pass. So we plug this into the formula. This will give us an approximate of how many milligrams of this substance remains. And this is getting me about 12.1 milligrams. Okay, question 9. These two questions, 9 and 10, were the kind of random questions from chapter 7 that we had to fit in to this unit. So number 9 is from 7.4, finding the first partial derivatives. So we'll do the first partial derivative with respect to x. So if we're doing it with respect to x, that means y is just a coefficient or a constant value And if it's multiplying something, that makes it a coefficient. So this y is just a constant value. So if we're differentiating with respect to x, the partial derivative would differentiate just this portion that has the x variable. So the derivative of 4x squared is 8x. So it's 8x y. And then again, y cubed is a constant value. So we're only really differentiating the 9x squared, that is 18x, and then we multiply it by the y cubed. So it's minus 18x y cubed. And then the derivative of 4x with respect to x is 4. And then the derivative of y, since y is a constant, if we're doing the first partial derivative with respect to x, the derivative of a constant is 0. Now for the partial derivative with respect to y, now x variables are constant and y is the variable. So 4x squared really is no different than a constant coefficient like 5y or 10y. And the derivative of that would be that constant value. So the derivative of 4x squared y, the partial derivative with respect to y for that term is 4x squared. For the second term, we're differentiating this now, y to the third. The derivative of y to the third is 3y squared. That 3 is then going to multiply the 9 to make 27. So minus 27x squared y squared. The derivative of 4x, if we're doing a partial derivative with respect to y, is 0 because 4x is a constant. And the derivative of y is 1. Now for question 10, this one is from 7.5. And what I talked about in class is I don't want you to worry about memorizing. There was a lot of things to memorize in 7.5, or some things to remember in order to successfully solve this. One of them was this value d that will help you determine if your critical point is a relative minimum or a relative maximum. So d was equal to the second partial derivative, the product of these two second partial derivatives minus this partial derivative squared. So that's one thing to remember. The other thing, or that you'll need to know, is now, okay, what is, depending on the value of d, what does that mean? So there were 3 criteria points. So if d is bigger than 0, and this second partial derivative is greater than 0, then your critical point is a minimum. If d is bigger than 0 and that second partial derivative is less than 0, it's a maximum. If d is less than 0, then it's what's known as a saddle point. It's not an extreme value. It's not a relative minimum or a relative maximum. So those are the things that'll be either on the board during the test, or I'll embed them into the question so you won't have to try to remember those. So what you first need, remember the way to do this is find that critical point. That's going to come from the first partial derivatives. So we first need that first partial derivative. So that's 2x. This is a constant value, so it's 0. Plus 16. That's going to be 0, and that's going to be 0. So it's 2x plus 16. The first partial derivative with respect to y, that's going to be 0. This is 4y. That's going to be 0. This is minus 8. And that's going to be 0. So it's 4y minus 8. Now we set each of those equal to 0. and solve. So here we get x equals negative 8. Here we get y equals 2. So critical point is negative 8, comma 2. Now we have to figure out the value of d. Before we do that, though, we need that second partial derivative. We need that second partial derivative. So if we look at this and do another partial derivative with respect to x, that's just going to be 2. If we look at this one and do another partial derivative with respect to y, it's going to be 4. And then we also need this partial derivative. So first we take a partial derivative with respect to x. That's what happened here. And then we take a partial derivative with respect to y. So if we look at these two terms and do a partial derivative with respect to y, it's both going to be 0. 0 plus 0 equals 0. So we need all three of those first partial derivatives, second partial derivatives rather. So now we can use this formula here for d. That's going to be 2. This is going to be 4. This one's going to be 0. So we have 2 times 4 minus 0 squared is equal to 8. So d is bigger than 0. This partial derivative is bigger than 0. So we conclude that it's a minimum value. So the critical point we had represents a critical point that's a minimum value, but this is an xy coordinate in three-dimensional space because we have a function with x, y, and z. So now the final result is to say that the relative minimum, we know it's a minimum because the value of d is bigger than 0 and this second partial derivative is bigger than 0. The relative minimum needs to be given as a point in three-dimensional space. We have the x-coordinate of negative 8. We have the y-coordinate of 2. But we don't have the z-coordinate. That z-coordinate is going to come from evaluating the original function for when x equals negative 8 and y equals 2. So if you plug negative 8 in for all the x values, plug 2 in for all the y values, add everything up, you're going to get negative 64. So this represents the point on the three-dimensional graph, x negative 8, y is 2, z negative 64, and its relative minimum value.